Zeal Education Society, redefining excellence.
Hello, good morning to everyone and welcome to my lecture, Basic Electrical Engineering, the EMF Equation of the Transformer. Myself, Dr. Mahadev Unde, Zeal College of Engineering and Research, Pune. So in this video lecture, we are going to learn the EMF equation of transformer. Okay, so here we know that when the AC supply is fed to the primary winding, it produces the flux, and this flux links to the primary winding as well to the secondary winding via core. Then according to Faraday's laws of electromagnetic induction, EMF is induced in the primary winding due to self-induction, and EMF get induced in the secondary winding due to mutual induction. Here it is assumed that the flux in the core varies sinusoidally. So let us draw the waveform for the sinusoidally varying flux. See this is T or time axis or theta axis, x axis, y axis is the flux. This is the origin. Now this is one cycle. Okay, the phi equal to phi max sine omega t. Now this is 0, and here it is, the flux becomes maximum when the time is t by 4 equal to 1 upon 4f. Okay, so let n1 number of turns on primary side, n2 number of turns on secondary side, phi high max maximum flux in the core, that is equal to B max into A, where A is the area of cross section of the core, F supply frequency in hertz, then E1 capital E1 EMF induced in primary winding, and E2 EMF induced in secondary winding, Now, as stated earlier, here it is assumed that flux in the core varies sinusoidally. So, as shown in the figure, okay, this is flux waveform. Okay, so the flux becomes maximum, flux changes 0 to maximum value in time dt equal to t by 4, that is quarter cycle, and t is periodic time, t is nothing but 1 upon f, that is it is 1 upon 4f second. Therefore, change in flux d phi equal to phi m minus 0 equal to phi m, and dt time required to change this flux from 0 to max equal to 1 upon 4f second. Then according to Faraday's laws of electromagnetic induction, the average EMF induced per term equal to d phi by dt equal to phi m upon 1 upon 4f equal to 4 phi m into f. Okay, but as the flux varies sinusoidally, the form factor Kf equal to RMS value divided by average value equal to 1.11, and therefore RMS value of EMF per term equal to 4.4 multiplied by 1.11 into pi m into f. So it is equal to 4.44 pi m into f. So this is the RMS value of EMF per term. Okay. Therefore, EMF generated in a primary winding having N1 turns. EMF in primary winding having N1 turns equal to capital E1 equal to EMF per turn multiplied by N1, and therefore E1 equal to 4.44 phi m f into N1. This is equation 3. Similarly, EMF in secondary winding equal to E2 equal to 4.44 phi m f into volt. This is also volt. So this is equation 4. Okay. Now, so this is the EMF equation of the transformer. This is the EMF equation of the transformer. Okay. Now let us see the transformation ratio. Transformation ratio K. Transformation ratio K. Now consider okay, this is the core and the windings are like this. Okay, so here it is, the sense of current is like this. So this is I1 coming back, supply voltage is V1, and on this side, so here it is load, this is V2 terminal voltage, so this is I2, and this is the direction of current. Then for this direction of current, it generates north pole here, and therefore the direction of flux would be like this. Okay, so this one is primary winding, this one is secondary winding. Okay, so the EMF generated here in the primary winding is E1, and EMF generated in the secondary winding is E2. Just now we have seen, and V1 and V2 are the terminal voltages. Okay, and I1, I2 are the respective currents. Then from equation 3 and 4, E2 upon E1 equal to N2 upon N1. This can be written as V2 upon V1 and I1 upon I2 equal to K where K is the transformation ratio. Okay. Now, when K is greater than 1, that is K is greater than 1, that is N2 is greater than N1, step up transformer. Similarly, when K is less than 1, when K will be less than 1, then N2 is less than N1, we can say it is a step down transformer. And when K equal to 1, so N2 equal to N1, it is a 1-to-1 transformer used in electronic circuit for the isolation of the circuits. Okay, so step up and step down transformers are used in the power system. Step up transformer to transmit the large block of power over a long distance from generating station to the load centers, whereas step down transformers are used at the consumer's end to reduce the voltage to the consumer's equipment level. Okay, then we can go for the kVA rating. kVA rating of the transformer. See, the kVA rating of the transformer is it depends on it is nothing but a product of voltage and the current. It may be either on primary side or secondary side without exceeding the standard temperature rise. Therefore, kVA into 10 raised equal to kVA equal to V1 I1 upon 1000 equal to V2 I2 upon 1000. So this can be written as V1 I1 equal to V2 I2 equal to kVA into 10 raised to 3. And therefore, primary full load current I1, so I1 equal to kVA into 10 raised to 3 divided by V1. Similarly, I2 equal to kVA into 10 raised to 3 divided by V2. So in this way we can obtain the current in the transformer. Now let us have one example. Consider the step up transformer, say 250/3000 volt single phase 50 Hz transformer has maximum flux density Bm equal to 1.2 Tesla in the core and EMF per turn equal to 8. Calculate primary and secondary turns and area of cross section of the core. Okay, so here solution. See, this one is considered as a E1, this is E2. So what is E1? E1 is nothing but EMF per turn multiplied by N1, number of turns. Okay, this is 250 equal to EMF per turn is 8 multiplied by N1, and therefore N1 equal to, you can use the calculation. See, 250 divided by 8, that is 31.25, but we cannot take the fractional and therefore it is 32 turns. 32 is the correct answer. Similarly, we can find out, see, E2 equal to EMF per turn multiplied by N2. So it is 3000 equal to 8 multiplied by N2. Therefore, N2 equal to 3000 divided by 8, that is 375. So number of turns on the secondary side is 375 and on primary side 32. Now the second question is the flux density. Okay, so the EMF equation can be written as, say, E equal to 4.44 pi m F. See, if you consider the E1, it will be N1. Okay, and remember that the EMF per turns remain same whether it is on primary side or secondary side, or whether it is on LV side or HV side, it will remain same. Now here this Bmax can be replaced by see, pi max can be replaced by Bmax into A. So what is E1? E1 equal to 250, 4.44 multiplied by Bmax. Bmax is 1.2 into A multiplied by frequency 50 multiplied by 32. And therefore area of cross section equal to 250 divided by into bracket 4.44 multiplied by 1.2 multiplied by 50 multiplied by 32 bracket complete equal to, this is 0.03 meter square. Okay, let us have an example 2. Okay, say the 80 kVA comma 1000 oblique 250 volt single phase 50 hertz transformer. Find primary and secondary full load current. Okay, so the solution is, pay attention, the kV rating is given to you, and this one is primary, this is secondary. Okay, so this will be V1, this can be considered as a V2. So already we have stated the kVA into 10 raised to 3 equal to V1 I1 equal to V2 I2. Okay, so this is our V1, this is our V2. Okay, therefore I1 equal to kVA 80 into 10 raised to 3 divided by, what is V1? V1 is 1000, so it is 80 ampere. Okay, similarly I2 equal to 80 into 10 raised to 3 divided by 250 equal to, this will be 4 times. Okay, 322 ampere. Okay, because here, see, if you go N2 upon R, N2 upon N1 equal to I1 upon I2 equal to K, and what is K in this case? 1 by 4. So K is 1 by 4. See, I1 is 80 divided by I2 equal to 1 by 4. Therefore take this I2 here and I2 equal to 320 ampere. So by various means we can find out the answer. Okay, so in this way we have finished this video lecture containing the EMF equation of the single phase transformer, then the transformation ratio, the kVA rating of the transformer, and how to find the number of turns on the winding and the area of cross section of the core, as well how to find the primary and secondary full load current. We will stop here. Thank you very much.